Well, hello friends, and welcome back to another code tour. Today we're going to go through the file system in Serenity, and specifically we're going to look at the ext2 file system, and I think we'll just start at boot, and we'll look at all the file system specific initialization, and then we'll look at how files are read, written, created, deleted, stuff like that. And so we're gonna specifically look at ext2 because there are other file systems in the kernel, but let's focus on that one because it's the most mature one. So when we first enter the kernel in the C++ world, we end up here in this function called init. If you've watched the startup process code tour, then you already seen this, and we set up everything to get ready for multitasking, and then once we're ready for multitasking, we spawn the second stage in it, which runs as a separate process or separate thread in the kernel. There's actually not super much need to do this. I just did it because it was neat. But anyway, in this second stage of init, we start to interact with the disks and stuff. So the first thing that we do is we just run all of this code to look for a hard drive and then look for like a root partition on the hard drive, and you can specify the root partition that you want on the kernel command line, but for now let's just assume that we find one and then we have it stored here in root dev. This is our root device, which is a disk device, and then down here we try to create an ext2fs object and we pass it the root device. And if we fail to initialize this object, then we will say we can't open the root file system and we'll hang. So it's not possible to progress past this point unless we have a valid ext2 file system. And then the first thing that we do with that is that we call mount root on this object called the VFS. And the VFS, it's the virtual file system, and it's like this abstraction layer that represents the file system starting at / and then everything that's mounted inside of it. In order to get to the right place, when you have like a path and you want to open whatever's in that path, then you have to go via the VFS, because the VFS knows about all the mounts and stuff for everything that's mounted, and it knows about all of the kernel devices. So basically all file access goes through the VFS object, and this is where the VFS receives its root file system. So, but let's look more into the ext2. So when we first create this thing, it's pretty simple. Not much is happening here. In the constructor, you can see that we're calling up to a base class constructor called DiskbackFS, and this is currently it's still only used by the ext2fs, but the idea here is to share stuff that's common for any file system, stuff like caching and flushing of, like coalescing and flushing of writes, stuff like that. We can do that in a shared implementation so that if you want to add a new file system, then you'll just inherit from DiskbackFS and you'll get some amount of functionality for free. So in DiskbackFS, we'll find stuff like the block cache, which is called disk cache here, and it's not terribly important for this particular code tour, but basically there's a cache of blocks so that when you try to access the disk, then first thing we do is we look in the disk cache and see, can we satisfy your block request from the cache, and if so, we don't have to go to disk at all. Anyways, but the interesting stuff happens when we call ext2fs initialize, which, as you saw in init, was happening right after we constructed. So in initialize here, the very first thing that we do is we read out this thing from the ext2 file system called the superblock. And the superblock is a very important data structure in the ext2 file system. It has all of the metadata about the file system, and we just read it verbatim from the disk, and it has all of these fields and things, and basically it tells you everything you need to know about this file system in order to start reading from it or writing to it. And we stash that superblock away here in a member So that, because we want to keep reading from this thing and modifying this thing all the time, so it's better to just keep it around in a permanent member in the ext2 file system. And then here, this is like a little old and weird. Don't need to do things this way. But basically, we're just getting the super block. This should just be a simple getter. Yeah. So there's some old stuff lying around here still. But then the first thing that we check is that the super block magic field has the right magic number. This just tells the kernel that, yeah, this is indeed a ext2 file system. And then we extract various parameters from the super block, like what's the block size of this file system, how many block groups are there, and then we read from disk, we read out this thing called the block group descriptor table. So an ext2 file system, by the way, the reason that we use ext2 is just because it's simple, and it's pretty easy to understand, easy to implement, and it's also compatible. Like ext3 and ext4 are backwards compatible with ext2, so it seemed pretty reasonable to start using ext2, and then we can add additional features and eventually end up having like ext3 or 4 support as well. But right now we only support even a subset of the ext2 capabilities. So this thing has a long way to go, but it does kind of work. But anyway, so the way that ext2 file systems are organized is that you have this thing called, it's divided into blocks, and the file system has a block size. And in our case, let's see, so we have a test file system. We can just see what it looks like here. It has a block size of 1 kilobyte. So that's what we're working with. And then everything in the ext2 data structures, they always reference block numbers. And then you know that the offset into the disk is like the block number times the block size. And the file system is organized into this thing called block groups. So in our case, we have 8,192 blocks in each group. And I don't know where to look here. I guess I would have expected to see how many groups we have. Anyway, it doesn't say here, but you can calculate like how many groups you have in the system and so on, and then you know how big your block group descriptor table is. Because in each block group descriptor table, you'll find all this metadata about the blocks in that group, and also inodes belong to a specific block group. But it's possible to have, like, you can have an inode in a block group, and the inode itself contains blocks from another block group. This is just sort of it's sort of a lazy association. I'm not really sure how to describe it. I think the idea is that you want to spread things out in a logical way so that stuff is likely to end up close to each other on disk, which of course was a more important concern back when you had like spinning platter hard drives, and it's much less important nowadays with SSDs. So this is definitely a file system organized for the spinning platters era. But anyways, I'm not like a big file systems guy or anything, but I've understood. I've got a pretty decent understanding of this file system in particular because I've been implementing it. So in the block descriptor tables, block group descriptor tables, you'll find the bitmaps for the allocation state of all the blocks in that group and all the inodes in that group. And those bitmaps are a very important part of creating and deleting files and so on, because whenever you want to make a file bigger than it currently is, then you need to allocate a block to put the new data in. And in order to allocate a block, you have to go and consult the block allocation bitmaps, and those live in the various block group descriptors. And yeah, and we can look at the allocation algorithm when we get to that. But for now, basically, we're just reading, when we're initializing the ext2fs object here, we are just fetching the superblock, and then we're fetching, computing some stuff based on the superblock data, just to have it on hand, like the block size. And then we read out the block group descriptors and cache those away in this thing called the block group descriptor table, which is the cache that we have of that. Okay, anyway. So, why am I getting stuck in my brain? So at this point, we have initialized this and everything's good. So we call mount root. Let's look at mount root. So if you already have a root in your VFS, then you can't mount another one. So that will be a failure. In fact, maybe we should detect that failure here. Like if this fails, it failed. That would be very bad. Anyway, so what we do is we create this object called a mount, which is basically a mount is an object that tells you where in the host file system is this thing mounted and what is the guest file system that's mounted here. So we have an inode identifier for the host and one for the guest. And inode identifier is this VFS concept in the kernel, and then it contains a file system ID and an inode index. And that's how you are able to reference any file anywhere in the VFS, because many file systems may be mounted in the VFS, but every file system that you mount gets its own unique file system ID, the FS ID, and then in each file system, every inode has a unique ID as well, and that's the inode index. So this represents a unique inode anywhere in the VFS. So mount is a host inode identifier and a guest inode identifier. So for instance, when we were mounting the root, let's see, then we are creating a mount with no path, I guess, because the root is special. So the mount has no host or guest location really. It only has a guest because the ext2fs that we're passing in here, this is the guest. But in the root case, it's less interesting. Anyways, let's just plow ahead because I haven't looked at this for a while, but the root inode has to be a directory. That makes sense. Oh, right. Yeah. So each file system. So every file system has a root inode. It's a virtual function that you have to implement in your FS subclass. And in the ext2 case, root inode, it's simple because it's always a hard-coded inode number. It's number 2, I think, yeah. So we can always say for any ext2fs, the root inode identifier is going to be an identifier with this file system ID and the hard-coded root inode number 2. So that's how mount root knows which inode to mount there, because he grabs the inode ID and then he asks this file system, hey, get me the inode with the root inode ID. Checks that it's a directory, which will be true for /, and then it becomes the VFS root inode. So I think after that point, we'll immediately notice if this didn't work out, because the very first thing that we do then is we load the kernel symbols, which is this text file that we have that contains all the symbols for the kernel so that we can do nice looking backtraces when things go bad. And that's loaded from the file system. So if we look in here, we'll see that it calls VFS open /kernel map. And I guess we can just see how that works. So when you call open, the very first thing that we do is that we try to resolve a path. And that's the incoming path here. So in our case, that was /kernel.map, right? Yeah. So if we just follow this, we'll see here, we call resolve path, and it's going to give us back a custody or an error. And I guess it's a good time to talk about what a custody is. So because many file systems, they only maintain like forward linkage, or whatever you want to call it, so that like you can go from a directory to its children, but you can't go from an arbitrary inode to its parent, because you don't know, like you don't know whose parent something. You don't know how to find someone's parent. It's not encoded in the disk data. So the only way that we know how to know who someone's parent is, because it's very important to us quite often in the kernel, is to remember how you open something. So what we do is we have this custom object called a custody, and a custody is it's called a custody because it's the relationship between a parent and a child. And in our case, the parent is ignore these names here, but it's a relationship between the name in the parent and the inode itself. So you would open a directory, say slash, and then you would want to get a custody for kernel.map in that directory. And what that does is that it allows you to associate the name kernel.map with a specific inode, and you can find the parent custody, and then you can walk up the custody chain up all the way up to the root. And for instance, that's how you are able to figure out like what is the absolute path of an open file, because each open file will have a custody associated with it, and then you can just look at the custody and walk the chain of parents. And I can show you, I guess, how absolute path is implemented. So we just walk the chain of custodies here and create a string where they are separated by slashes. That's how we compute the absolute path of a custody. This used to work very differently. I think custody is very, very similar to what many other kernels do, but I'm not exactly sure if it's the same, but it seems like a very obvious way of solving this problem. So where were we? Right, so the custody represents a parent-child relationship in the file system and allows you to go upwards toward the root of the file system, because every custody should be able to get you to the root if you just walk the parents. So when we call resolve path, it's going to give us a custody. So let's look at that. A resolve path is a slightly confusing function, I would say. It's takes me quite some time to get back into how this thing works. But essentially, we start by walking each component of the path. We divide the path into components by splitting it. Wherever we encounter a slash in the path, we just split there, and then we walk each of those path parts and try to work out okay, so we're in slash, and now we want, say, bin, right? And then we look in the slash directory for something called bin, and then say that we want bin slash, bin bash, right? Then we look for bin in slash, and then we find that, and it turns out, okay, this is the directory, and we have another component. Then we open the bin directory, and then we loop again, and now we're looking for bash in the bin directory, and so on. And this function here, this does all of that, and it figures out if something goes wrong along the way, like if there's some access denied issue, for instance, like say that you don't have executable permission on some part of the path along the way to what you want to read, then it will fail with eaccess. Or if you have a path that contains a directory that's not actually a directory, you might fail in that way, and so on. And it's also where mount transitions happen. So if we come across a path component that is actually a mount point, then we resolve that here as well. So there's all these things here going on. And of course, we as we create this path resolution, we do it in the form of a chain of custodies. So for every step along the way, we create get or create. So there's a custody cache that a custody may come out of a cache. And that's just to make path resolution way, way faster, because if we already have a custody for something, then we don't have to create it. But basically, and actually this could be exploited further to make path resolution faster, now that I think about it. But it's just not something that I've spent much time on. But we create this chain of custody objects along the way, and eventually, if we find the thing that we're looking for, then we return the last member of the chain of custodies, which will be like the leaf of the thing that you're accessing, that you're trying to resolve. Oh, and by the way, we also do symlink resolution here. Anyways, we wanted to look at open, so but that's what we do there. So we resolve the path, and then we look at the various options of open, if it's like, are we being told to create a file, and so on. But assuming that we just plow all the way through, we look at all the different flags and figure out, like, if this is, do we want to only write into this file? Then, wait, what the heck does this even say? Oh, no, it's read permission. Then we check, like, do you want to read? Are you allowed to read? If not, then we fail with the XS. Do you want to only write? Are you allowed to write? And so on. And this part of open here is where devices are taken care of. So if you have a /dev entry, for instance, if we go in /dev, you see that all of these files here in /dev, they have these major and minor device numbers. And this is where this gets hooked up. So if you open something that's actually a device file, then the VFS will go and get the actual device object. So we call it get device on this static, public static thing, which will give you a device pointer if there is such a device with this major and minor number. And if there is, then it will create a file descriptor for you that refers to that device. Otherwise, it will fail, because it's possible to make a device node that would not be real. Like, we can make our own here. Fake character device, major 99, minor 99. So now we have this thing here, fake, right? And if we try to cat fake, it would just say fail to open, no such device. And that's this error right here. So we make it all the way here that we are trying to open a device file, but when we look it up, we can't find it, so we fail. And then the thing that open will actually return is either it will return some error code, or it will return a primed file description object. So that's the very last thing we do if everything succeeds, is we create a file description, either referring to a device or one that just refers to the custody, which contains an inode inside of it. So where the heck were we? Load ksims. So yeah, so we want to load /kernel map. So as I was trying to describe there, first we resolve the path by opening the VFS root. We find this. We always start here at /, and then we find this name immediately in the root directory, hopefully, and then this here, actually, this argument to open is the base starting point, like where we will start searching, so that if you had a relative path like this, or like // or whatever, and then it would start in this custody and then walk from there. That's how that works. So I guess then we could look at how read and write works. So if we look at, let's look at the syscalls, for instance. So we have sysread. The way that sysread will work is that it operates on a file descriptor, obviously, because that's what you pass it, and it will just get the internal file description object for that FD, and if everything looks good, it will block if necessary, but eventually we'll get to this point where we try to read from the description, and then depending on the type of file that this FD refers to, we call different implementations of read, but say that it's an inode, then we call inode read bytes. And inode, by the way, is a separate object in the kernel, so I guess I skipped over something there that I shouldn't have. If we go back to VFS open, when we are resolving the path and we're creating the custody object, this here is a chain of custodies. Like that's a bit, maybe that's not super obvious, but like this, the custody always has a parent chain that goes all the way up to the root. But the custody itself represents the thing that you're looking for, the inode that you're looking for, and the name of that inode in its parent. So the file description that you're creating here, it will now contain enough information to find the inode. So you can see here that we're passing a custody and we end up creating a file description that is a wrapper around an inode file that we create with the custody inode. And an inode, oops, this is an interesting object. So inode is the second most important, or perhaps the most important object in the file system implementation. So file system is 1, or FS. I don't know why it's called FS. Maybe we should rename it to file system. Anyway, this is what ext2fs inherits from. It's the base class for any file system that you would want to implement. And then it represents like the whole file system. And then an inode is the child object of the file system. It represents one single unit of either a file, a directory, a device, whatever. Like one inode in the file system is represented by an inode object. And these things are not eagerly instantiated, so of course you can have more inodes on the disk than we have inode objects in memory. And they kind of come and go. And we keep some of them around if we think that it's going to be used soon and stuff like that. But basically, an inode represents an inode on disk. And in the ext2 case, we have ext2fs inode, which inherits from inode. But when we were looking at the file description, when we create one of these guys, then we're creating a file description that's a wrapper around an inode file. An inode file is a file subclass, and file represents anything that can be inside of a file description. So anything that you can open with a syscall to open, you can represent with a file. So this is inherited by all these different things like device, FIFO, inode file, watcher, shared memory, socket, and tracer. And yeah, we create one of those and we pass in the inode, and then we can read from this guy. That's what we end up doing. So when we call this, is called to read. Sysread. Then we're calling read on the description, which is the file description for this FD. We call read. We turn around here and we call file read, which will end up in ext2, inode file read. And here, this is an ext2fs inode at this moment, and we'll call it read bytes on it, passing in the current offset of the file description, the count, which is how many bytes we want to read, buffer we want to read to, and a pointer to the description, because that might come in handy. And this is the implementation that we're interested in right now. We can see we have these other file systems here as well that all have their own inode subclasses. And this here is the read bytes implementation in the ext2 file system. So this here is the workhorse function that does the reading from disk. And of course, the first thing it does is just lock the inode. And file system blocking in Serenity is very overly aggressive at the moment. It's something that definitely needs improvement. But right now we're just super paranoid. We just lock, like totally lock the inode, or totally lock even the whole file system whenever we want to do something, even if we just want to read. So there's a lot of arguing over these locks. And then, of course, if we are reading from an empty inode, we can tell you right away that we're going to read 0 bytes. So it's just a shortcut for that. And then there's this little quirk in ext2.fs where if you have a symlink that's shorter than 60 characters, then it will be stored in the block array of the inode rather than having an actual block allocated for it. So it's just a way to avoid allocating a block for symlinks. So we have to look at that and see, is this a symlink file, which will mean that the symlink bits are set in the mode bits for the file. And then is the size less than the max inline symlink length? Shorter than 60 characters. Now I'm actually getting a little paranoid here, because is this correct? Shouldn't it be this way? I'm not sure. I'm going to take a note of this and look into it later. Come on, Gnote. Stuff to look into. 60 characters for symlinks in the block array. What is 60 correct? Yep. Well, it's always good to do this. Anyways, if it is one of these fast path symlinks or whatever, then we can just, when you want to read from it, we can just memcopy out the data directly from the block array, because every inode in the ext2.fs has a block array, which is just a list of blocks that contain the data for this inode. And it's right here in the raw inode, which is the raw data structure that contains, this is like the raw data structure stored on disk, and it has the mode of the inode, the size of it, access times, and so on. And it also has an array here of block indexes, and it will contain a bunch of entries, and we'll get more into that in a moment. But basically, we can just know that if it's a symlink and the size of it is short enough, then this is not a block list, but it's rather a special storage for the symlink target. Okay, so next thing that we do after determining that, well, I guess it was not a symlink shorter than 60 characters, then we have to actually, so this is read bytes, right? So we want to figure out, okay, fine, where do we read all these bytes from disk then? And then what we want to do is we want to make sure that we get the block list for this inode. And the block list in ext2.fs, it's basically all of the data for a file is stored in blocks, right? And they can be anywhere on the disk. So we got to figure out which blocks contain the data for this particular file. And we do that by looking in that block list array that I was just showing you. But it's laid out in a kind of a convoluted way, because for small files it's very simple, because the first couple of blocks are just stored right there. Their indexes are stored right there in this array. But then if your file gets a bit bigger, I think, yeah, you have up to 12 blocks directly stored in the array. So in our case, since our file system is 1 kilobyte per block, then if it's like 12 kilobytes or less, then we only have to care about these like direct blocks. But then if you want to have a bigger file, then we also have this thing called the indirect block, which is comes right after the 12th block, I guess. And the way that one works is that instead of pointing to a block of data, it points to a block with pointers to blocks. So there's one layer of indirection. So when we're getting the block list for an inode, we first get all the direct blocks, and then we look, do we have any indirect blocks? if so, we have to go through, we have to load that block with all the indirect pointers, and then we add those to the block list. And then there's this thing called doubly indirect blocks, where there's 2 levels of indirection. So the doubly indirect block in the inode points to a block that has pointers to blocks with pointers to data blocks. So there is also a triply indirect blocks, which is 3 levels of indirection. So this is how you're able to store pretty large files on the file system. It's just that there's this layer, levels of indirection that go on. And this code is, I feel like it could probably be structured in a better way. And the implementation is definitely not perfect here, but it seems to kind of work. So, yeah. Anyways, I want to look at read bytes, but we compute. Wait, this is the wrong file. ext2. Here, we just compute the block list and then we cache that in M block list, because computing the block list for big files, it often means that you have to read a whole bunch of stuff from the disk. So if we've done this once, we don't want to do it over and over. So we just cache it. And it's a cached vector here in the ext2 file system inode class. So each inode will cache its block list on first access. And then basically we compute, because this is read bytes, so we have to compute like what's the first block in this inode, like the first logical block of this inode that we want to read from, what's the last logical block, and then we loop over from the first logical block to the last logical block, and read out, here we call read block, which reads a block with a specific index from the file system, and we read it into this stack allocated buffer here, and then we copy from this buffer out to the users, or from to the buffer that we were provided. So there's a little bit of a copying going on here, but since it sort of has to be done this way, or you could do it differently, but there's the issue that you might not be starting at the boundary of a block, right? You can be starting a read somewhere in the middle of a block. So that's why we do this in 2 steps. So we read the block from the file system, store it here, and then we take the part that you want, and we actually copy that out to you, to the out pointer, which is here, the out pointer. And I guess we can look at fs read block, because that will go directly to DiskbackFS, right? So this is what I was talking about earlier. ext2fs class doesn't have any own implementation of read block. It just inherits it from DiskbackFS. And then here it might use cache. And if so, it will be quite a lot faster. But you can go and look at this yourself if you're interested. This is a little bit outside of the scope of this particular video. But yeah, so reading is actually pretty simple, because we just have to get the current block list and then read the relevant blocks, and then we're basically done. But writing is a bit more complicated. So let me show you. So when we get the write syscall, then we call do write. Let's see. It's, it does a bunch of things, but eventually figures out that it wants to call description write. So it's right here next to file description read, we have file description write, which we'll call file write. And in this case as well, we end up in inode file, and we call write bytes instead of read bytes. And notice here, we also, if we ended up writing any bytes to this file, we also make sure to set the modification time of the inode. But let's go and look at write bytes. So here again, we have this logic with symlink first. So if what we're going to write is going to be smaller than the symlink length, This doesn't seem entirely right, though. This doesn't seem right if init is already bigger than max inline symlink. I'm gonna have to go and fix that out, because yeah. But the idea here is that if you are writing out a symlink and you're within the range of the optimization where we don't allocate a block, then we just write whatever you want to write. We'll just store it directly into the block array again here. So, but if this is not the case, then we go down here, and now the very important for when you're writing is that writing can increase the size of an inode. So the first thing that we do is we just grab the old size and then we compute the new size. So after this write, is the inode going to grow? And if it does, then we have to resize it. So we call resize with the new size, and of course it will just succeed right away if you're resizing to the same size. But here is where all the really fun stuff happens. So if we need more blocks after the resize than we needed before, then we compute how many more blocks do we need, and if we don't have that many blocks according to the super block, then we can say right away, dude, I don't have space, and the write will fail. But otherwise we carry on. And so first thing we do is we just get the current block list, and then if we need more blocks after the resize than we needed before, then we call allocate blocks, passing it the number of blocks that we need, which is how many do we need after the resize minus how many did we need before. That's how many more blocks we need now. And then we just add those to the end of the block list. But this is just a vector here, so we're not storing anything on disk now, just to be clear. We're just adding those to the vector of blocks. And then I wonder if this is really correct. Okay, blocks. Well, anyway, assuming that this is correct. So this is if we needed more blocks after than before. Otherwise, there's the other scenario where we need fewer blocks after than we needed before. That means that inode is shrinking for whatever reason. Now, that's not going to happen when we're doing it right, but it might happen if you call truncate. So we have to take care of that scenario. And in that case, what we do is we just keep going until we have as many blocks in the block list as we need after the resize, and then we pop from the back of the block list and set the allocation state of each block as we go to not allocated. And then the next thing we do is this block list that we have now massaged into the right size, we write it out to disk as the canonical block list for this inode. So, and then we mark the inode as dirty and so on. And I guess maybe we should look at how allocate blocks works. So basically, when you call allocate blocks, you're giving it a group index. This is the block group index, or the index of the block group, because the system is divided into block groups. But it's just a preferred index, but it will try to allocate blocks from the same block group as much as possible. But once we run out of blocks in that block group, then we'll give up and allocate from anywhere. And this is just how many blocks that we want, and then we just loop here. So we loop calling allocate block, preferably from this group, and add to this vector, and then return the vector. And this thing could definitely be written in a more efficient way. Like you could look for contiguous sequences of blocks, for instance. We don't do that right now. And then allocate block works by, first thing we do here is we look up the preferred group. We get the group descriptor for the preferred group, we see if he has any free blocks. If so, we use that one. Otherwise, we look through all of the groups and check until we find one, and we stop there, right? And then after this has run, then group index is the index of the group that we're going to allocate out of. So then we get the group descriptor for that group index, and then we get the block bitmap for that specific block group, and then we create a wrapper bitmap object just to get access to this convenience function here, find first unset, which will just scan this bitmap block looking for the first 0, and once we find it, we will set that particular block to allocated, which means we'll flip that 0 to a 1, and then return the index of that block in the bitmap as the return value. So whoever was calling us allocate blocks, he gets the index. We found a 0 somewhere in a suitable block bitmap. You get the index, you add the index to the vector here of block indices that we eventually end up returning from allocate blocks. And there's a little bit more to it than that, because when we write out the block list, this is also, it also takes me some time to switch my brain into how this thing works. But basically, the trick to this whole thing is that when you're writing out the first direct blocks, it's very easy because you just write them into the block array, one dot 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 dot. But then when it comes to the indirect blocks, then you have to allocate one block to put all the block pointers into, and then when it comes to the doubly indirect, you have to allocate a block, and then you have to allocate another block just for the metadata of like eventually pointing to some data block. And this function here, write block list for inode, takes care of all that. And we actually stop before we get to the triply indirect because that's not implemented yet. So that's a fix me. But I think we can do 2 GB files or something like that. But if you want bigger, then we have to implement triply indirect. So to do, fix me, whatever. But yeah, so where were we? I was looking at write bytes in ext2 inode. Right, so after we resize the inode, so now it has the correct number of blocks allocated, then of course we want to have the block list, blah blah blah, compute the first logical block and last logical block in the inode that we're going to write to, and then there's a little bit special thing here that if you're writing somewhere into a file, but you're writing like halfway into an existing block, then in order to do that correctly, we have to first read out that block from the disk, and then like put your changes into that copy of what's on the disk, and then write the whole thing back to the disk, just to make sure that whatever was there before is still there if you're not overwriting the whole block. So that's why this loop here is a little bit more complicated than the read bytes loop because of that. Although it does feel like this is a little too big, and it could probably be done in a more clever way. But eventually, what we do is like we read a block from the disk if you're doing a partial block write, or we just don't read from disk. We just take like an empty block and copy in your data that you want to write into it, and then write that out to disk. But everything funnels here into fs write block, which again is in DiskbackFS, which interacts with the disk cache and so on. And it's a little outside of the scope of this video, but basically when you're writing bytes to an inode, then it's a loop over the logical blocks that you want to write to, and each step in the loop calls fs write block. And then once you have written everything out to disk, then if the size has changed, then we call this notification that the inode size has changed, And this is notifies the virtual memory system in the kernel, so that anyone who has like memory mapped this file, if the size has changed, then it's good for them to find out, because then they can adjust their boundaries and stuff. And likewise, if the contents of an inode has changed, then we also notify the VM system so that it can take the appropriate actions. But yeah, so that's how read and write work. I guess we can also look at how creating a new file works. So that would be ext2fs create inode. Or let's go to syscreat. Oh, I guess that's actually sysopen with ocreat. So if you're opening a file and you pass the create flag because you want to create a new file, then we end up calling VFS create instead. And it's similar to open, but we actually check that the permissions are right, and can I write to this directory that I'm trying to create a file into, and so on. And if everything checks out, then we call create inode on the file system of the directory that you're trying to create an inode in. And we're giving it the base name of the file that you're trying to create and the mode that you want to create the file with. So then we can go and look at create inode. Create inode. And so what we do here is, first thing, we look up the parent, and we also, let's see how this works. When we want to create an inode, then we allow you to specify how big you think the inode is going to be, and then we can fail right away if we know that we don't have space for it. So that happens first, and then we try to allocate an inode, because the file system has a finite number of inodes. So this may not succeed, but if it doesn't, then we return enode space. If you run df, no, it doesn't show here, but we can probably check it in procdf. Yeah, so if we look at this ext2 file system, we can see that there is a total inode count of 128,000, and we have 117K free inodes at the moment. So plenty of opportunity to create new files. But you will eventually run out if you create more. So that can fail here. And allocate inode works very much like allocate block, because it's laid out in the same way that each block group descriptor has an inode bitmap, and then you just have to look for a 0 in that bitmap to find an available inode. And you can have a preferred group that you want to allocate your inode from, but often we don't care. Like in this case, we just allocate inode 0. I think we could do something like try to allocate in the same group as the parent directory, but right now we don't do anything like that. We just allocate anywhere, basically. What do we do with the expected size? Needed blocks. Is suitable. It looks like we'll refuse to. Oh, this doesn't seem right. We shouldn't refuse to allocate inode if there is no group can house the whole thing. In this cases, we should just spread it across multiple groups. So there's a bug. It seems like we're going to fail if we don't have enough free blocks in an individual group to house the whole inode. So, but I think very often this is not happening in practice at the moment, because we basically never pass it any other size than 0, except maybe for directories. Yeah, when we create a directory, then we pass in 1 block size as the size. So we're never gonna, this is not gonna be a problem in practice at the moment, but it's something that we should fix for the future. So just adding some fixed means here. So again, if allocating an inode fails, then we enode space. And then this note here is accurate. So allocating an inode, it just gives us the inode ID of an available inode, but it doesn't actually flip the bit yet. So maybe this thing should have a different name. Because allocate block actually flips the bit. But this one doesn't. So yeah, I should probably change the name of allocate inodes since it behaves differently than allocate block. Okay. And then we try to add we're creating an inode, right? So we have a name and we have a parent. So we try to create an entry in the parent inode because the parent is a directory. So we try to add a child to it with this name. And if that doesn't work, then we fail because there might already be something in this directory that has the same name, and then we want to fail. But if this succeeds, then the parent inode now contains a reference to the new inode. So at this point, now we are like committed to going through with this. And then we allocate blocks for this inode. So we know how many blocks we need. That's the size of the inode divided by the block size. And at this point, this is where we flip the inode allocation bit to 1. And and this also actually set inode allocation state will also update the super block and the block group descriptors because they also contain these counters. So the super block has this global counter, like how many blocks are available, how many inodes are available, and then each individual block group descriptor also contains that same information, like how many blocks are available in this group. Oops. So after we set the inode allocation state, now we're super duper committed because we've entered it into a directory and we've also taken the inode in the bitmap. Now we just create the actual ext2 inode data structure that we're going to write to disk. So we populate this thing with the mode, the user ID, the size, and so on. All of this stuff, we just set these appropriate values. The current access time, what is that, C time, creation time? The modification time, they're all populated by a call to get time of day. So they just get the current timestamp. And yeah, if we're doing a device, then we store the device numbers in the block array. This is how it seems to work. I sort of reverse engineered this by just looking at my file system in a hex dump because I couldn't find this information anywhere, but it appears that device numbers are stored in the block array, and it's different depending on if it's a character or block device. And then after we've created all of this metadata, we write out the block list, and then we write out the metadata. And then just in case so the ext2 file system has an inode cache, which just maps from an inode number to an inode object. And this is just to make it faster to look something up by inode index. And if we do a lookup where an inode index is not like an allocated inode, then we actually put a null in this cache just to make it fast. Next time you ask for the same thing, then we can tell you right away, hey, we don't have this inode. But now that we've created an inode with this number, we just make sure that it's no longer in the cache under a null or with a null value. So, and then we call get inode, which will actually populate this cache, and then we return the inode. So get inode is just this function that checks the inode cache for this entry. If we find it, return it. Otherwise, if the inode is not even allocated in the inode bitmaps, then we say, okay, like I was just saying, this inode index is not a real inode. Cache it as a null value, return null, and then otherwise, get inode has to actually go and read the block containing this inode from disk and makes an entry in the inode cache. There's a lookup here in between. That's a bit weird. Why does it do a lookup again? I guess it thinks that it may have changed since last time. But we're holding the lock the whole time, so I think this extra lookup here is unnecessary. Fix me. Really need to check the cache once again. We've been holding mlock this whole time. But yeah, so we create an ext2fs inode object. And we copy in the raw inode that we read from the disk into the ext2fs inode object. And that's that. And we set it in the cache so that next time you can get to the fast path up here where we just find it cached. That's how creating an inode works. I guess we can also look at deleting an inode. So this is unlink. If you call the unlink syscall, then we call VFS unlink. Again, we have to resolve a path, and if we don't find it or if something is not accessible to us for whatever reason, we fail. But if we find the thing and we're allowed to delete it, then we call remove child on the parent inode of the thing that we're trying to unlink. So what that will do is that, let's go look at the ext2 file system. So we end up in ext2fs inode remove child, and basically a directory in the ext2fs is just like any other inode, except it has the directory bit and it has a special file format for the data. So the directory is stored in a sort of like a run length encoded array, if you will. And there's also a hash table format that we don't support yet, but basically it's just this big blob of file name, file type, inode number, and what else? Yeah, I guess that's it. File name, inode number, and file type. And here, when you want to remove something, then we have to go through the directory and create a new version of the directory data that's stored on disk, and like make a new version of it that doesn't have the thing that you're removing. So we just recreate it without that entry, and that's it. So, oops. The way we do that is that we create a vector of directory entry objects, and then we traverse this directory inode, skipping over anything with the name that we're deleting. And then if it's not the name we're deleting, we're appending it, and then we write out the directory with the entries. So this is like every entry except the one that you wanted to delete. And then I should also mention that inodes have a lookup cache, and the lookup cache is only used by directory inodes. And it's like a hash map of name to inode index. And this is used so when you try to look up like what's like the inode index for the file bash in the inode that represents the /bin directory, and then you can, if you've populated this cache, then you don't need to scan the directory data on disk, but you can just directly query this hash map. But of course, when we're removing a file, then we have to remove it from this hash map. So that happens here, and we can also quickly look it up, like, is this even one of our children? Like, do we have a child with this name? We don't have to read from disk to figure that out. We can just ask the lookup cache. I don't know why this thing is here. This could just be here. But yeah, that's pretty good. And I guess we can, the one thing that we can talk about is link counts. So inodes, they work in this weird way because every inode has a number of links to it, and when the link counter drops to 0, then the inode has no more references. It's like a reference count, and when it drops to 0, that's when we can actually delete it from disk. But as long as the inode has a non-zero link count, then it has to, someone somewhere in the file system is pointing to it. But you would have to scan the whole file system to find out who's doing it. This all works out because we just, when we unlink it from somewhere, the same exact inode might be also a child of a different directory. So this may or may not cause the file to get deleted. And you can see here, when we decrement the link count, then we see if the link count reaches 0, then we call uncache inode, which means that we remove it from the file system's inode cache. And let's see, when that happens, then we end up deleting the inode object, ext2fs inode. And in the destructor for this object, if the link counter is 0, then we call free inode. But notice that if an inode object in the kernel can get destroyed with a non-zero link count, and then it will just not do anything. But if the link count reaches 0 when we uncache this object in the kernel, because there is no more references in the file system, no more references in the kernel, then we can free the inode from the file system, which then goes and writes over the dtime, I guess. I don't know why we have to do that. I think maybe that's for the file system checker program, FSCK, that expects this, I think. But anyway, when we free an inode, then we just grab the block list and then we go through it and mark all of the blocks as no longer allocated. And we mark the inode index as no longer allocated. And if it is a directory, then we also update the block group descriptor saying this block group now has one more, one less directory in it. Sorry. Okay, so I think we've just been through that interesting things, like looked at how files are opened, how they are created, read, written, and deleted. And I've been going so fast, but I hope that this made sense. And I hope that you were able to tag along here, and I hope that there was something interesting. But I really encourage you to look around the system. All the source code is obviously available on GitHub. And it's really not that complicated if you just sit and look at it, and it works. It's Unix-like, right? So if you understand how Unix works, then you can use your intuition about that to navigate around this really, really well. And you might find bugs and inconsistencies, and then we can fix those things because this system aims to be Unix-like. So anyways, I think this is going to be it for this video, because my brain is so tired from talking. But yeah, I hope you were able to understand most of what I was talking about, and I hope you found it interesting. And please leave some suggestion if there's another code tour that you want in the future. And other than that, thanks for hanging out and checking this out, and I will see you next time.